5 o'clock. Welcome, everybody. This is a bit of a milestone. This is my last lecture for the course today. So just to remind you, we're sort of doing Unit 7, and Yoni's going to swoop in and finish off with Unit 8, which is the not really fun stuff with the machine learning. So we thought we better let Yoni do something other than just course administration, let him do something fun. So we're here today. I'll give 2 hours and talk about data frames, this kind of thing. And tomorrow we have an excellent opportunity to see Anna Ferglin come in and give a perspective seminar. So we're looking forward to that. I'll be on campus tomorrow to sort of introduce her and stuff. So we'll see you then. Yeah. So yeah, we also have Project 3 coming along, and there's a couple practicals for this. And there's obviously Project 3, which has to do with both the content I'm presenting here with the data and the data frames, and then you're going to use that data and do some kind of basic machine learning tasks. So that's kind of fun. So I did sort of begin this the other day. We'll skip sort of the introduction and just we'll talk again about relations and move on. Okay. If people have like questions about earlier content, I'm not sure if we're going to have time to cover it, but maybe at the end of this spare time we can discuss some strategies with the project or something. But hopefully we won't be bored. Okay, so if you remember the other day, I spoke briefly about databases. So a database is like a system that keeps track of all the data, right? And you can like ask it what data's in there, and you can tell it to set some data to some value. And it's like a machine which sort of does what it's told. And sort of the most popular way of dealing with data and databases is through what's called relational algebra. So a relation is sort of like a mathematical function, but it's more of a generalization of that, where you have a relationship between multiple variables. So a functional relationship is like, given X, I can compute Y with some function F, for example. And a function might have 2 inputs. So you might be able to compute Z as a function of X and Y or something like that. But not all things in maths are functional relationships. Some other relationships, they're not like 1 to 1. They're like 1 to many, where you have say the square root function, like the square root of 4 could be plus or minus 2, right? So normally we talk about the square root in maths as being the positive branch of that, but if you could define, say, an equation like this, and this equation defines a relation, not a function, right? Well, it's a function from Y to X, but it's not a function from X to Y. So there's a special, like we kind of think of this kind of thing with the brackets around it as a tuple, and you'll see tuples in Julia all the time, right? We use the same parentheses as in maths to denote tuples in Julia. Also the same way of calling a function. We use the standard maths notation. And you can kind of think in Julia and in relational algebra of this little object here, which is like a tuple with nothing in it. Okay, and so this is a little interesting curiosity, because there's actually 2 relations over the tuples with nothing in it. There's the empty set, and there's the set with a single tuple in it. All right, which is a bit of like a pedantic kind of thing, but you know that's the tuple in Julia, right? And I could have like a set containing I don't know, one of these, or maybe the empty version of that, right? And they're 2 different things, and you sort of have the same thing in relational algebra. There are systems out there where they kind of like use this as a kind of Boolean algebra where it's the empty set is false and the filled set is true, and that kind of works out nicely when you're dealing with your joins and stuff. There's but yeah, just going back down to ground, like in terms of SQL, in terms of databases that we use in everyday life. So a data in a database has to be finite. It has to fit on the hard drives, right? So we're not so interested in like abstract mathematical relations. We're interested in finite discrete relations where you might have 3 columns and 10 rows or something like that, right? And you can fit all the disk in a file on your data on a file on your disk or something. Some databases are so big that you actually have a whole fleet of computers and they each store a small shard of the data, and only together will the system behave as a coherent kind of database. So like if you have lots of data, you might have to use one of those systems one day. But yeah, so most databases, like SQL databases, they're not like strictly relational. Like relational algebra, for example, talks about sets, whereas you might have 2 of the same row in some databases, right? So it's not like there's no, you might add a uniqueness constraint to your database, but it doesn't have to have a, but it depends on the database. Some databases, you know, require primary keys, for example. Okay, so here's an example of a relation, right? So you have 3 columns, like and each row is like a tuple with 3 things in it, like a name, a birth date, and something which is adult. And this is an interesting one. So for example, there's a functional relationship between birth date and is adult. If you know the birth date, you can just calculate, are they younger or older than 18 years old? And I can see I have data from a year ago and I haven't updated it. So that's interesting. But but also this one, there might be like a further relationship where like the name might be unique and you use that to look up that column, or there might be like an ID column that you put in and it might be some ID number that the database can look up really quickly. And so a lot of databases will use ID numbers, or they'll use UUIDs or some other kind of hash or something to kind of look up data. And so the primary way that you'd look up a row is called the primary key. And you might have secondary keys, which are like other uniqueness constraints and things that might define a row. So why are people interested in this? So this relational algebra is really important and has been really important from the 70s onwards. Basically, only more recently has anything really come back to compete with it. But the reason for it is the relational algebra lets you define relationships between different data sets in a neat way. In particular, so you have data which relates to another, but the relational databases, they let you really keep everything consistent so that like if you change one part of the system, everything else changes in sync and you don't have to think about it. So there's this process called normalization where you take something you want to represent. So make sure, let's say you have some profile like a LinkedIn profile here. Right, it's a complicated kind of thing. Your Facebook page is a complicated kind of thing with lots of different bits of data in it. And the relational database does this thing where, well, it allows you to store your data in a normalized form where every fact is only stored in one row in one table. Okay, and so if you want to change a fact, you only change it in one place, and then all the queries about that will link everything together, right? And you use a series of constraints and different things in the database to make sure it's all consistent at all times. So this is from a book about databases, and like you can imagine there's a table with the user ID, and you might know their name and last name and so on. And so, for example, this, you know, maybe when Bill Gates created this profile, he was William Gates or something. And so what William Gates could do is log in as his user and then ask the database to change his first name to Bill. And like the rest of the data and the rest of the profile won't need changing, right? If for example, when you see this view on the website, it's going to query this row and it's going to get this thing. And so if you update it in one place, nothing else is going to change. And then there's all these relationships. So you might have a preset series of industries and regions and different things. And like, rather than sort of say that Bill Gates is in the greater Seattle region, you might say, you might have a table, a separate table for the regions, right? And then what you can do is you can much easier search for all the people, say, in the same region or something like that, because it's faster for the database to like look up everything with the same integer rather than look up all these different strings, and people might spell the strings slightly differently. So if you use Facebook or LinkedIn or whatever, and you type in, say, your employer or something to LinkedIn, it'll actually, you type a few characters and suddenly it'll come up with a list of things you can click, and there'll be a table somewhere in LinkedIn with like the list of all the employers of the string that's sort of like the string you typed, and then they might sort it from proximity from where it thinks you are and things like that. And then there are different types of joins. So like, you know, a person might belong to one region, but they may have many previous jobs and many items of their educational history, right? And so in these tables, you have an ID column and a foreign key column. So there's like, say, 2 rows where Bill Gates has had 2 positions, you know, co-founder of Microsoft, and then the Bill and Melinda Gates Foundation. So, and so here, if Bill Gates wants to add a 3rd job, you just add an extra row to this table, and then suddenly everything else in the system would update. Okay. Yeah. So the way, once this data is stored in this form on disk, you sort of, there's a sort of unofficial standard way of getting all this data. Everyone uses a language called SQL. So it's a very old language, much older than me. And it sort of looks a bit different to a lot of programming languages you've seen. In fact, when it was written, it wasn't really written for like nerdy programmers. It was written for more business people to sort of be able to look at their data. So they decided to make the language read a little bit more like English. So it's like select user ID from users, where users is like the name of the table, for example. So if we imagine this table up here, this would give us, it would ignore all the rest of the columns. It would give us those first 3 columns of this table. Now that might be a lot of data. So you might, for example, you might already know the user ID because someone's logged in or something. You've clicked on something, you know the user ID of that person. And so you might filter that down just to 1 row. And a SQL database will be really good at just extracting that 1 row really fast while it's doing lots of other different things in parallel. Okay. So that's how you can build like one of these big web systems and have lots of people logged in at the same time and all, you know, updating their Facebook posts and all these different things. Because the database is really good at like, you know, getting little pinpoints of data and updating little pinpoints of data, like making all these small transactions. And these type of databases are called transactional databases, and they're good at that. The kind of stuff we do as mathematicians and not as like software engineers, like what we're going to do as mathematicians, is going to be more what we call analytical data processing. And there might be analytical databases that are better at doing big queries involving millions of rows and things. So the important part of relational algebra, this idea of you have relationships between tables and you use this join operation to take 2 columns which overlap in some way. So if we want to like figure out the jobs of someone, you would join the user with the positions, right? So that's like, make sure the value in this column is the same as the value of that column here in that table. But that would be, there's a problem with that. If you ran that, you may sort of crash your system entirely, because you can imagine there's a lot of users and they all have a lot of positions, and it was going to try and return, you know, gigabytes of data perhaps, or terabytes of data if it's really is actually linked in. And so actually like just typing in a query like that can actually be dangerous to a production system. It's kind of interesting. You know, even getting read access to a production database, like database you know, system administrators and that are going to get a bit cagey about giving you that kind of access in case you do something like that. All right, so if you really want to do it, you would actually probably have a user in mind, and you'd then pinpoint that user and then find, you know, all the different positions that they were related to. And you use this join and the where together. The database will very quickly figure out how to do that. So internally, it's just keeping a few dictionary kind of indexes, and it'll just look up a couple of things and give you a couple of rows. Yeah. So I think I mentioned this last lecture. So this is sort of like very much standard in the field of data. You're going to be mathematicians or related from related fields, science fields, if you're in this course. So, you know, you're probably going to be involved with data at some point in your life. And so it's sort of a really good sort of obvious tool to have under your tool belt, that to actually understand SQL. I'm not going to cover it anymore though. I just wanted to sort of like talk about how you would get data out of some system when you're solving some problem. You'd use SQL, and you'd probably use those type of queries, and you'd get tables of data out. Yeah. Once you've got these sort of tables, you know, these are things that one thing you could do is download that data and put it in Excel. Okay. So I'm sure most of us have probably opened up Excel and like had to do some homework, or made a budget, or, you know, just added up some numbers or something, used it like a calculator in our lives, right? So as a sort of, you know, data scientist or this kind of thing, you might be tempted to use that. And it's fine, it's good, it's useful. It's actually really useful to know how to use Excel well. But we're going to use more programmatic tools designed for this purpose, for data analysts, for data scientists, for these kind of roles, typically called data frames. So languages, probably the two most famous languages which have data frames in them would be R. So the R is a statistical language, and out of the box, it sort of comes with data frames. It can open CSV files and things for you, okay? And you can do statistics on them. And then there's Python with its pandas package, okay? And so these are two really huge sort of ecosystems for manipulating these, and they both have data structures called data frames. Julia is a bit newer. They've sort of implemented a Julia data frames package. Works, you know, conceptually very similarly to these other packages. And, you know, it's obviously taken a lot of the learnings from things that already existed and like implemented all the good stuff for you. So what is a data frame? So data tends to come in rows, which might be, say, observations you've made in reality or something, and columns. The columns are sometimes called variables or features. And so like typically a row describes a sort of a single thing, a single item, a single event that has occurred or something like that. And the column is like contains some attribute about that event or that thing in the world that you're describing, right? And so generally within a column, everything has a given kind of like data type. So there might be a name column, and you'd expect that to be string data, and there might be like a birth date column, and that might be like a date, you know. So you'd expect everything within a column to have the same data type, but over the different columns, you have different data types. So this is why this is sometimes called heterogeneous data. So like in Julia, what's a good example of this? You might have like an array that's sort of homogeneous, it has all the same things, but you might also might create out like maybe a good example is like a tuple, you know, and that might have 3 different data types in it, and that's sort of heterogeneous data. In this case, the Julia compiler kind of actually knows what the 3 different types are. If you put it in an array, it sort of knows it's an array with 3 of anything in it, and when you start processing those things, it has to kind of like figure out what the type is before it does something with it, so it slows it down a bit. So one thing the data frames package will do is like deal with all those speed considerations for you, so you don't have to. Okay, let's get started. So there's a file, athlete-events.csv. I don't even know, you might be able to, oh yeah, you can just download it from Kaggle. I'm not sure if we ever host it on our website, but you can definitely get it from Kaggle. And it's a history of competitors in the Commonwealth, in the Olympic Games, sorry. And it's just a decent data set. It's a medium-sized data set, it's 40 megabytes. And so it becomes a little bit awkward to work with this data in Excel. Like certainly an Excel professional would handle it fine, but it's sort of nice to be able to deal with it programmatically. It's small enough that when you do things at the REPL, it'll be fast, but it's big enough that it's a pain to kind of like look through row by row and do things by hand. Okay, so, but just keep in mind a data set of this size would have been challenging in the 80s. Like I remember the first computer I had a 40 megabyte hard drive. So right? My friend, and the computer before that, it used a cassette tape for storage, you know, so it's back then that would be like the stuff we're going to do today would have been actually challenging to kind of like for a professional to do unless they had a really good sort of computer. So we've sort of seen CSV and JSON files in Unit 3. I think Paul mentioned like different ways data stored, and probably started looking a little bit at data frames. So we're going to like load this file into data frames and maybe some other packages just to explain that there's a bit of variety. Yeah. So let's get cracking. So we have this CSV file. So let's just have a look at it for a minute. So if I open the CSV file, it's got all these different columns and things in it. So the first row is called the header. It contains all the names of the columns. And the next row has comma separated values, which is why it's called a CSV file. So it has an ID column, like names, sex, age, height. And so that's sort of what we're going to look at. And you can load that into Julia, as I did a little bit earlier, using this CSV package. So this is like using CSV. You have to do that to be able to use this. Oh, no, sorry, that's just opening the file and showing the first lines like I did with less. Now we can use a package called CSV to actually load this data like this. Sorry. We can load this. I'll try and make this somewhat practical. If we get behind time, I'll skip this part, but I think it's worth sort of seeing what goes on. So it's just taking a moment to actually compile the CSV file, and then it'll take like a quarter of a second or something to read it. So there's, you can see the 271,000 rows, and it's just spat out a summary of the first, say, 10 and the last 10 or something. That's what we see here. Okay. Now that's a little bit awkward and ugly to deal with. That's what that object is, that CSV file object is a lazy wrap around the file. If you go and ask for row 100, it'll have to like go and get that from disk and load it for you. So we're actually going to load that into RAM as a data frame and have a look at that. Okay. So let's just do that. And here we go. And so now it's looking a little bit more tabular. So we've got row numbers, the ID column, and all these other things. Okay. So what's going on here? What's something you can notice with the ID column? What's it the ID of? So it's not the ID of the row, it's actually the ID of the athlete. Okay. So why would you want to do that? Can anyone think of a reason why you might need this column, for example? Yeah. Yeah, to make it to keep track of each athlete in a different table. Yep. And two athletes might have the same name. So that's really important. So a lot of systems will have something like this where the normal name or like a human would use to identify with something, it's not actually globally unique. So your database would probably create like an ID column so that you can be unambiguous. That's cool. That's excellent. So you can see at the REPL, you can kind of get this data frame and look at it. We'll go through here and we'll kind of see what we can do. Like data frames have a size. They kind of behave like they're two-dimensional objects where they have a number of rows and a number of columns, a bit like a matrix. But unlike a matrix, it's heterogeneous. Like the data types in the different cells might be different. And you can use this names function to get out the names of the columns if you need them for something. You got like the first function, so you can get like the first 10 rows of a database. That's a nice little thing to do if you just want to like take a subset of your data and fiddle with it. Maybe you have lots of rows and it takes ages to do the processing, so maybe you want to just play with it with a tiny bit of data, or you just want to look at it. But there's a last function as well, so first and last, very similar. And you can use this sort of indexing pattern here. So let's have a look at this. If we copy that and put it in the REPL, what we're going to get Here's the first 10 rows. You can kind of see it's omitted some columns while printing this, but that's all the rows. There's no like dots in the middle like up here, right? So that's really useful. But similarly, you can also like put in a list of you could put in like I just want the I don't know, the sex column or something. And you put that there, and that thing is a symbol in Julia. I think you can use a string too. I think it doesn't actually care. So internally, it's using a symbol for speed, but it does let you use strings wherever you want. So it's sort of like a very user-friendly package, this one. There's like, there might be more than one way to do the same thing, so you can do whatever's most sort of ergonomic at the time. Yeah, so you can index it in 2D, sort of like pretend like it's a matrix. You can get a single column, just going dot, pretend it's like a struct, and you can just get some column out of it. So that's really neat. So you can just play with the vectors. Now notice this is like a strongly typed vector in Julia. So if you want to play with that vector now that's out of the data frame, that's going to happen at full speed, just like if you're doing any other data processing in Julia. You can get like the height. Now, what do you notice about this one? Well, there's this missing data. So some records, historical records especially, if we go back in time, we're actually talking about 1900 and 1920 for those two rows. So back then, no one actually recorded the height and the weight of those athletes, which is interesting, I guess. Yeah. So there's this thing in Julia. I don't know if missing's been covered, but I'll just do it. So there's this thing called missing. It's a bit like nothing. Remember we had nothing? It had a type. And it was this capital nothing. There's a type of missing as well, and it's a struct with no data in it, 0 bytes, and it's there to like represent data which doesn't exist. So you don't know, it's some unknown value. And the nice thing about missing is you can do stuff with it, and it'll propagate the missingness for you. All right. So if you don't know some value and you want to add some value you don't know, well, you still don't know the answer. Does that make sense? So it sort of represents a state of knowledge, like about that variable. It's missing data. I have no knowledge about it. So, and you'll find things like maximum of like 1, 2 missing. Like it'll propagate everywhere basically, because you don't know whether that missing value is 3 or -1, right? Like depending on what it is, it may or may not be the maximum value. So it sort of propagates. You can do let's do some things. Let's count how many of the heights are missing. So let's have a look. So we're getting the height column out here, right? And then if you remember this dot, this is the broadcasting operation. So for each of those elements, we're going to ask, is it missing? So is missing is a function that returns. So that's not a missing thing, but this thing is a missing thing, right? It returns true or false. And then we're going to count them. Okay. So count is a function which returns the number of true values. We're using this piping syntax. This is very popular with data frame kind of processing. If you remember what this does, is it takes this thing, calculates it, and then calls the function on the right with it. That's what the pipe does. Okay. You might want to do things like count the number of unique IDs. So how many different athletes are there? So remember there was, how many rows were there? $271,000 rows, and there's only 135,000 athletes. So on average, people go to the Olympics twice, I guess, which is interesting. So this is the kind of thing you'll do as a sort of a professional data scientist, is you're going to do this thing called data exploration, and you're just going to get some data set, and you're going to use functions like this to figure out little bits of factoids about the data. And just so you sort of get familiar with what's in it. So there's this nice function in data frames called unique. Well, unique built into Julia. So it's kind of like you have some values, it creates a unique set of them, but it's overloaded for data frames where you can tell it which columns to be unique on. So this could be more than one column, depending on your data, right? It will create a data frame, it'll just take like the first row or something as representative of that set of rows with that unique identifier. I can't remember if it uses first or last logic, but either way. For things like the height and weight, hopefully it's not too important. Like we just get one sample per person, but we'll see. Probably the team hasn't changed, that kind of thing. But who knows? Things could change. You definitely get older. You may or may not get heavier. Cool. So now we've sort of done a little bit of exploration. We're becoming a little bit more familiar with it. Let's do a little bit more analysis with it. Let's ask, of the 135,000 people, how many are men and how many are women, for example? Well, it's 100,000 men and 33,000 women, so it's a little bit unbalanced. And we'll really dig into this a little bit later. Okay, like plot that versus time and things, and we'll sort of understand that a bit deeper. So that's a little bit wordy, this one. Like some operations I find in Julia, like it's a pretty simple thing you want to do. Note this nice syntax. There's a lot of curried functions in Julia where you can like create a function which compares with M, all right, and things like that. And so sometimes you can find tools which are a little bit more concise or a little bit more maybe logical or easier to think about. So there's this package called split apply combine. This is actually a package I wrote, but I'll show you anyway because it's kind of neat. It has these functions. It has like these group functions, right? Group count. It has a few different functions, and probably my favorite one, or the one that I like using most, is group count. So it just sort of like, given some columns, right? Find the group count of that. Now you could imagine this was fine for M and F, male and female, but if you wanted to do that per country, you'd want to do something a bit more programmatic. You wouldn't want to like create this for every country, right? So group count will actually figure out all the keys for you from the data and tell you like how many different things are coming from different countries. Now, I can't really tell from this which is the most sort of populous country or one that contributes the most competitors, because there's lots of rows here, 1,000 rows, and there's these dots here where most of the data set in. But what I can do is I can actually sort that. And it goes in ascending order, right? So we're looking at the bottom. So United States has actually contributed the most people. Okay, so this is the kind of functions you'll use just to explore data and just learn things about it and do analysis. So most people going to the Olympics are apparently American males. Not most, because there's actually hundreds of thousands of them, but that's still a kind of a bias, I suppose. There's a group function which will let you not just in the group what's the count, it will let you actually figure out other things. So like you know, what's the names of all the people from China? Well, those names are now in this array, for example. And that's a nice little function. Okay, so there's some nice little functions in split apply combine, and those functions were written because Julia doesn't have functions like that in the base library for things like vectors, right? What has existed and existed in R and existed in pandas and exists in data frames is a data frame specific function called group by. And so this is a really neat function, and you'll probably use it a lot. So rather than dealing with like dictionaries and vectors in Julia, you've got this data frame, and the data frames library knows how to do grouping for you. So you can actually do these things, these group counts and stuff that I was showing you with the data frames. I was just showing you them before because it's sort of a more fundamental concept about grouping data, right? It's not such a tabular concept as a just data concept. And so here we could like group by athletes by team. And what is it giving? Oh, it's giving us the first group. Okay. So this is actually, I'm gonna do this at the REPL because I find the HTML rendering that it makes a little bit hard to read, but we forgot to build the athlete data frame. So let's go up to that. Just bear with me. This is going to be worth it. Hurrah. Let's create that. All right. So there's GDF group data frame. And it's actually a collection of data for sub data frames or groups of data frame. All right. So it has this first group, which is like China, and like that's like some rows of the table, right? And then there's another group. Well, actually, there's multiple Chinese teams. The Olympics started before the communist revolution, for example. So, but like you can go like, I think you can get like different groups out of this, like this. And kind of like look up groups and get these little data. Oh no. Oh, I don't know. I thought there were ways of doing something like that. But you can definitely like iterate them or something. Is that right? Oh yeah, you can iterate them, right? So you can like collect, you know, and I can get like maybe I can get the 10th one or something and get some other group for some other country. Yeah. Cool. So once you have these groups, you can do things to each group. So that's generally what you do. We'll get back to the workflow for using group a little bit. But let's just continue with the, oh no, hang on, sorry. I'm getting twisted because I'm just getting behind on the new. All right, what time have we got? This is cool. Nice and sweet. So now we have this group data frame. We want to ungroup it or combine it together into things. And so there's this function combine, which is like the opposite of grouping. And it takes that group's data frame and lets you do things. Now there's this really neat syntax that they do in data frames, which is kind of cool. So normally this thing in Julia is an operator that creates pairs. So let's just have a look at that just real quick, just to show you. So I could have like 1 goes to 2 or something. And where these pairs get used is dictionaries. This kind of thing. So I have a dictionary that creates these different mappings, and I can like take that dictionary and look up element 2, right? And it gives me element at the end of the value 3, right? And so this thing itself, like anything in Julia, it's an operator, it's also a type, it's an alias for pair. And that's pretty cool. But they use it like this little, like it looks like an arrow. So it's sort of like we take the we take nrow, which I think is a built-in thing in GDF, and we rename it the count column. Okay. So this is like something specific to data frames, that when you have a group data frame, you have this number of rows. Yeah. And that lets you kind of like create this little table with all the different sizes of the things. And have I done this again? Actually, I should show you the sorting of data frames because that's really important. We can definitely go ahead. So what do we call that? Okay, so let's call that, I don't know, count data frame or something. And we can probably sort, we should be able to sort that by count, I think, and do things like that. And then we can again see, you know, America's the most, you know, contributed the most athletes. So yeah, just, I guess these are tools. It's where there's lots of different little ways of using them, and as a sort of professional, you kind of get used to like all these different little functions, and you get really fast at like getting into some data and taking it apart and putting it back together. Which, yeah, I love data, so that can be a lot of fun. It can be a bit like you know, stressful too sometimes, but you know. Okay, so row and column based storage. Okay. So we talked a lot about data frames, but I didn't really explain what a data frame is, right? So those transactional relational databases I spoke about, when they have data, they keep each row as a piece of data on disk. Okay, and you can delete a row and insert a row, and that's how it gets stored. There's a bunch of bytes together, and that's a row. But there are other ways of storing a database, or a relational database, or a column base is like with columns. So you'd have, instead of having like each row of the database has like a tuple. You'd have like a single collection of vectors, and each vector has just that one column's worth of data. And so these columnar databases, columnar tables, they are worse at doing these transactional workloads, but better at doing analytical workloads. If you want to do analysis, it's actually better and faster to use this kind of format. The reason they're bad at transactional stuff is if you want to update one row, you have to go to all the columns and update each of those column vectors. So you might have to update like 14 different column vectors at 14 different places on disk, and that will be a lot slower and more fault prone and stuff than if you just have to update one. But for analysis, if you want to find like the mean height or something, it's much faster if all the heights are like all together in memory or on disk as just one little array, and then you can just zip through it really fast instead of having to go through each row and then find the offset to the height and then get that, and then, and so on and so forth. So it's very interesting. The way that data frames are stored is like this notation of like almost like as a struct with vectors in it. Well, actually, as it's stored in memory, it is sort of like a struct with vectors in it. It's a bit more dynamic than a struct because you can rename it and stuff. But and so even though it's stored this way, you can like ask for each row of the data frame and get like the first row and things like that. You can do like a for loop over each row. There's a name tuple iterator now that's come out in dataframes 1.4. If you want to do that but faster, it's sort of just a performance hack. But yeah, like I said, it often presents itself more as a two-dimensional container. It's not really a 1D collection of columns, which are 1D things. It's not really a 1D collection of rows, each with different columns in it. It's sort of almost like a two-dimensional container. Right. So as I said before, like iterating through rows means it's going to get all those different pieces of data from different places and put it together in a single row. So for data frames, this can actually be slower than operating with columns. So often if you're doing analysis, you get the columns out, you compare them column-wise and stuff. All those functions like group and combine and all that, they do all the fast way for you automatically. So you don't have to think about it. Yeah. So as I said, one thing you can do in Julia are these things called name tuples. So they're a lot like tuples, but each column gets a name as a symbol. And so, for example, what you could do directly from the CSV file is you can load all these things as into a row by row format. But it's relatively fast. It's sort of name tuples of things. And you kind of actually even know the type of each element in the name tuple. So it's actually pretty fast to do it this way. And so even without data frames, you can load in, say, a CSV file in a format like this, and then just use basic Julia vector kind of operations, right? So this is definitely another valid way of doing things. And there's nothing wrong with that. If you have some problem and row oriented is better, you just need to do that. It's all sort of built in. So, it's good because it's out of the box. You don't need any packages to do that. It just works. There's a package called type tables. I'm just going to mention it. It's almost a kind of alternative to data frames. Again, it's using columnar storage, but it's sort of like it's really doubling down on rows and name tuples kind of idea. So it's sort of like this one, but it's really stored in columnar format, and you can kind of iterate through it and everything. I'm sort of just saying that because there are alternative ways of doing things than are presented. So there's like a million ways to skin a cat, as they say. So yeah. All right. Another really cool package, and there's a few packages like it, is like query.jl. And so this is really fun. So they've kind of got like this little language you use with macros. And let's see if it has some examples. You get some data frame, and you can use these little macros in it, and it will let you kind of write things. And if you remember what we were seeing from SQL before, these kind of almost look a bit like SQL. You can kind of like just do things in that kind of way. So there's like so many different ways. Like data is like such a big field, and there's so many people interested, and there's lots of good packages for manipulating data. And in Julia, at least, they all work together. So like you can use query on top of data frames, for example. Load the data with CSV, put it in a data frame, and then use query to do your analysis. So that's a really kind of like promising way of dealing with things, I suppose. Let me just see. I think it might be worth having a little break here. And then after the break, I'm going to go through and I'm going to talk again about sort of the fundamental operations you want to do on data frames. Just because it's really important to have these skills of being able to get data and manipulate the data. And then we're going to do some analysis on this data set, which will have a little surprise, a little twist at the end. So it'll be kind of interesting. So yeah, it is currently 5:46, so I will come back and talk at 5:56 if everyone wants to have a little break. Thanks. If anyone has questions they want to throw in the chat, I'll take a look too. Yeah, you can look at it. I was asking why, you know, I didn't know this. Oh, bro, yeah, sorry, I'm speaking, bro. It's not that bro. It's cute, isn't this? So how long is it taking? Like, did you run it through the whole hour and then so do you think you could test it with just like 1 or 2 rows, like check code with a quick code, and then let it run half an hour? Yeah. So I don't know. I'm just more thinking, you know, so in my research career is just like spinning up 200 mosquitoes and then something around 18. So that code just and put it in a plot. Yeah, yeah. So you were sharing the code. Yeah, a plot. Yes, we'll kind of lead you around. You know, unless it's suspicious or nothing if someone investigates, but yeah. So I don't think like we don't have a sophisticated system. We run with which should be cool. We should do that. So you run it on the surface? Yeah. Mine runs under the power. Yeah, it's fine.
Hey, yeah, go ahead, shoot. So I'm getting my stuff. So obviously we've got the Excel right, that's not really much change. So that's the random variable. So what I change is or something like that. Yeah, so there should be a system product. Yeah, we don't have that. We have to get access now. It's good. Well, I can just check it. So I don't see Excel or rates, but I don't get it. It's not the nice. Maybe I don't. Internal. Because no, so an internal thing means someone's finished being served and they're going somewhere else, right? So when you finish being served somewhere, yeah, right, you have you get a column on that nature as well, right? I want to write off the key metrics, yeah. So I mean, and then somehow I pick which one to go to. Yeah, so you remember in my lectures, I think this thing where you have these different probabilities and now we're picking one of them. Yeah, like I got close to run sample, but that's what we did. Yeah, probably. We had like a sample function, but so it didn't get to stop. I mean, we watched it for a long time. Yeah, it was like maybe the end of it's not at the end of the lecture, it's in the this one. Yeah. So you have some P thing, right? And you have this. So actually, this one's really neat because you can kind of determine it. If you rewrite it, you can actually figure out that you're actually between the biggest one and one. I guess. I guess you check if I is larger than that, and then you can type it. No, then it's a lead event. Yeah. But like this is sort of an algorithm. There might be So something which is, can't remember. Maybe you have to use distributions. But yeah, it's definitely this range from CDFL is an algorithm that works as fast as yes. So I would need to use that mixed evaluation like that. Well, it's not about the arrival. Well, so it's more about like you have an event you're leaving somewhere. It's like what you do. Right? Yes. And then getting from A to B is changes. It's not so much of a rate of how long it takes to return arrival. Like, not like the external arrival. It's you can measure that rate if you want to, and external arrival the second but it's sort of like it's more about when you finish somewhere. So it's almost you try and reduce what you yeah, okay, so don't just go on duration. No, but once you get there, like there might be some time waiting in the queue or being served. Yeah, you have to check whether the queue's actually yeah, still yeah. 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 No worries. Okay. I think we're good. Let's get cracking. All right, everyone. We'll get back to this. So I'd probably just like to unless anyone has any questions or anything they want to ask before we move on. I'd like to just talk about data frames and how they work. So one important thing is look at this cheat sheet. Oh, this is very annoying. There we go. So this is a nice little PDF kind of thing. You can print it out if you're old school. And it talks about all the different functions that there are, like ways of creating them. The describe function is really cool. It gives like some summary statistics, ways of like doing certain operations, finding certain rows, indexing, dealing with missing data. And if I go to the next page, it'll have like joins and group bys and combines and stuff. Okay. So that's a really neat kind of thing. It's like you can print it out on a double-sided piece of paper and just keep it with you when you're doing project 3. You might find it handy. Yeah, but like that generally when you it's the kind of package you want where it has lots of functionality with lots of little different names, and you don't necessarily need to keep all that syntax in your head to be productive. You could just use a cheat sheet like this and sort of refer to it as you go. Yeah, so let's make one of these data frames and just have a look at it. So we got this data frame, right? So I can press df dot and press tab, and the rep will actually know what columns are in it, right? It has columns A and has column B. And in fact, if I dump this data frame, you can kind of see what's inside of it. There's a column lookup index, and there's the columns themselves. So there's an array of abstract vectors which contain the actual data. And that's all the data. That's where they are. And then here, this is a hash map. We don't really need to understand it. And then for each column, you can attach metadata and stuff. But we don't need that here either. But when you go df.a, what it does is it looks up this hash map for which index of this array is A, and then returns that array. Okay. That's how it kind of works. That's what it does, so to speak. You can obviously, well, not obviously, but just so you know, you can actually kind of mutate the thing. So you can add columns to it pretty easily.
So you can't do this to a struct in Julia. You can't just add a new field to a struct because it's sort of an immutable thing. Even the mutable structs, the names and the types of the fields are fixed. But this is a nice sort of dynamic structure, and you can use that property syntax to kind of manipulate it, which is kind of cool. And then, you know, you can obviously use this 2D kind of matrix-like syntax to get the first row and the column C, and you can do things like that, and that gives you that cell. So that can be useful. You might do that in a for loop or something. You might get an entire row using this sort of syntax, like that. So notice the type here. This is a data frame. This is a data frame row. So it sort of prints it like a data frame. It gives it a row number, but really it knows fundamentally that that thing is a scalar. And when you do something like that, it gives you a scalar thing back. Like a scalar, it knows it's a single row. So yeah, that doesn't return a vector anymore. It returns the actual value in that cell. You can, instead of using the property syntax, you can index it with the thing. And just like with matrices or whatever, you can use the colon to mean everything. Or you can like get a subset of rows and subset of columns, and you can use a syntax like that. So it's, you know, vaguely useful. Like it can be really useful sometimes. You might have calculated the indexes you're interested in. You might be interested in just a couple of columns. Then you have a small amount of data to look at and manipulate. So it can be nice sort of cut down the data you're looking at. Right. So that's sort of like a very basic thing of like, how's the data stored in it? How do you get to it? How do you change it? You can obviously, I didn't mention this, right? But you look at ds.c, you can obviously do things like, you can obviously mutate everything, right? And that's changed, right? Or you could do this here as well. And you can obviously use those mutation commands everywhere. One thing you might like to do is for example, filter, figure out a subset of rows. So there's a filter operation. This function works exactly like the filter on arrays. So imagine the data frame is a vector of rows, and you can apply a predicate to each row and filter it down and get a new data frame. Okay. You can even do this with an exclamation mark, and it will mutate it. So you're saving on RAM, and it's just mutating it in place. But then you lose the old data, so it's a bit more dangerous. When you're experimenting, exploring, you wouldn't tend to mutate it. You tend to create new copies of the data, so that when you're going to make a lot of mistakes when you first start out exploring. You're trying to write a script or something. So if you create new copies of the data, you can go back to where you were and run it again, and you don't have to like load the data from disk again, for example, to get it back to the original state. Now, data frames has a kind of like I mean, maybe this is fast now, actually, since 1.4, but data frames has this general syntax of using this arrow here, right? So you can take the column A and pass it into the isOdd function, and that can be your filter, right? And data frames will kind of like wrangle this thing and make that extremely fast, like as fast as would be possible. Okay. You can another really common way of indexing is using this pattern. Okay. So you'll see this a lot, for example, in Python pandas, you would always use this. So what is this doing? So this bit is creating a vector of trues and falses, or a bit vector, 1 and 0. True is kind of like 1 and false is kind of like 0. What this is saying is the first and third row is odd, has an odd A in them. And then when you use that, say, to index, if I can index, say, I can use that as an index of some vector, say like A, B, C. This is a general thing you can do in Julia. It doesn't have anything to do with data frames. And that's a way of picking picking certain elements from a vector. But you can also do the same thing, picking certain rows of a data frame in that way. And so that's That's something that's really common, is to write something like this so you can figure out, get some of the rows you're interested in. Yeah. Yeah, so I think I just explained that here. So basically, like, this is just like a compound way of like first figuring out which ones are odd or even and then indexing with those. There's a select thing. This is very much like in SQL. You can select certain columns, but I think it's a little bit more powerful. I think you can do things like, what is that? That's column C. I don't know, we could do like lowercase or something. We can make those strings lowercase. And I think it will, oh, maybe we need transform, sorry. Perhaps we need the there's a transform function that lets you do that, which is a bit more, oh, damn it. Maybe you have to do this. I can't remember how that works. I've got the example here though. In this one, you don't just select things, but you actually take a column and change it, and maybe even add a new column to the database here. So, and here you can see it's transforming multiple rows. In this one, we're adding a new column, mean B. We take the data from B, pass it through the mean function. So this is actually the entire column, not just that particular row's value of B. And then we put that into mean B. Now this is kind of okay. You've kind of got the same value here. Where you might like to really use that, and where that might be really powerful, is when you have group data frames. So you can imagine within the group, you might take a mean and then populate it here. And then you might, for example, take the difference to the mean or divide by the mean or something for every row, and then use that as a feature for some decision, like for ML or something. So this transform one, again, they have this general language where you take some column by name, you pass it through some function, and you get that. And so this by row thing is like a little wrapper, and it lets you apply that for each row instead of the entire collection. Okay. So remember why it's like this. So it's quick for data frames to get the B column from the data frame. That's a really fast operation. And so that's sort of the natural thing to do with the data frame. And that's why that kind of natural way of treating it is columnar. Whereas when you do by row, then you're sort of really dealing with each cell at a time. So just, if you haven't heard the term cell before, it's like Excel, like one of these things as a cell. Yeah, there we go. And then we're like making C lowercase. This is what I was trying to do before, but it didn't work. So I probably had to go something like this. Is that what I was complaining about? Yeah, there we go. See, I did something. That's interesting. It created new names based on the function name. That's fascinating. It must have realized it clashed or something. Cool. There's the group by thing. So we sort of touched on group by. So we can, this is where it starts becoming a little bit more sort of visible what's going on, I guess. So here's the group data frame. Oh, it's because I didn't mutate it. There's this transform here that mutates it. So now we can group by the oddness. And just to show that again, what that really is, it's like a collection of two miniature data frames or two sub data frames, one for each group, the odd group and the even group. You know, and this is like is odd is false group, which is the even A's, and then this is odd is true group, which is like the odd A's. Okay. Cool. Once you have this thing, you can use combine to like, so there's this common pattern, which is called split, apply, combine in data manipulation. So you often get data sets like our athletes thing. We'll see it. You might like split by country or something, and then take the mean of everyone in that country and then combine that back together into a single data frame. So the combine step is to take, you know, these number of sub-data frames and create, usually you create like one row per sub-data frame. So it's some summary data of those groups. You might, for each data frame, create a number of rows and then put it together into one table again. And so combine can do that too. Here, for example, we have these groups, and we can use combine to kind of like sum them together or something. And join's an interesting one. Join is a string operation. So let's have a look what it's done. It's taken our strings, which is A and C, and it's just join just concatenates strings together. That's what it does. It takes a list of strings and puts them together. And you can like join, this is something that's common. Like, let's say you're trying to create a CSV file. People often use a function like join. So that'll create ABC, but you can also like maybe join them with commas in between or something. And you can like 3D print lists of stuff that way. Yeah, so did I run that? Yeah, that's kind of cool. So like for each group, you kind of see the group column here, and you kind of have these summary statistics for that group, which might be like the sums and the means and things. But of course, it can be any computation you can think of, right? You can put any Julia function in there. So this is why data scientists and that like prefer to use Python or R or Julia for these kind of tasks, is because you can write your own logic for these kind of functions. Whereas if you're using SQL, it does have the ability to group and aggregate and reduce and things. But you're really limited to a very old and kludgy language for describing your logic. If your logic is more complicated than mean or sum or something, then it starts to get quite difficult. Okay, there's the inner join function. So imagine we had two tables now. So this is like the relational algebra, the SQL stuff we started with. You can take two data frames, and you might need to do this. Like we'll have a little look at project 3. You might need to like join together information from two different things. So you might have like people's names and ID, and you might have people's kind of ID and their occupation. Notice this is 1, 2, and 4. And you might want to do like an inner join. So this is like one of the join operations before SQL. So we kind of know that from this data, John Doe is a lawyer, okay? And so we get that out. And same way we have Jane Doe is a doctor. We don't know what Joe Blow is because there's no ID 3 in this column. And here, we don't know the name of the farmer. But the inner join is one where you get just the rows which match, okay? That's why it's called inner, because it's things that match. And if you match, it's like a set intersection kind of thing. And then there's other types of join, left joins, right joins, and full outer joins. And they let you deal with like, if the sets don't overlap, what do you do with the bits that aren't intersecting? And they let you deal with those. Cool. So like that was just sort of like a brain dump. Like this is a package, this is how you can use it, right? So it's not that fun. So what I really want to do is actually show you how to use these tools to actually get something useful or something non-obvious, okay? So we're going to do some analysis of athlete height. Okay, this at first might not seem very interesting, but we're going to actually ask some questions about athlete height. And we're going to do some exploration and we're going to find something out. So here, I think I still have this data frame in memory. So we should be able to run this, right? I have to run statistics. There's a package with all the means and medians and modes and things. All right, that's not very fun. It's missing, okay? So actually, you might use a function like skip missing, which is a little helper function, which lets you do that, right? And so we can get like all the male and female kind of heights, and you can kind of see, on average, the men are what, 10.5 centimeters taller than the women in the Olympics. Okay, so it's not too surprising, sort of. what you'd expect, I suppose. But we're going to ask another question, right? So not just what's the difference between men and women, but what's happened over time. So if I asked you, like this is data going all the way back to 1900. If I asked you the question, has athlete height changed over time? What do you think? So anyone in the room or in the chat do you think it's changed or do you think it's stayed the same? Why has it changed? Why? People are getting taller as time goes on. Anyone know why? Yeah. Yeah, better access to nutrition and things like that. So we're actually talking about a long time ago, 1900. It's well studied that, say, in the children from the Great Depression are shorter than they should otherwise be based on their parents and their children, and things like that. So generally, probably before 1800, it was probably most people who weren't rich were malnutritioned and didn't grow to the height they would if they were fed better. I don't know if that's the right date, but yeah, there was some date like that where, you know, life was a bit rougher than it is now, let's just say. Let's see. Cool, let's do it. So actually, this one's just this kind of data frames example of these two calculations. So here we're showing the group by and the combine operations. So let's just do that one at a time. So athlete by gender. This is going to give us a big data, two very large sub data frames, one for males and one for women. And then we can combine those, we can find statistics for each and combine them into a single table. And we can kind of see that. So that's a nice way of presenting your data, right? Like it's pretty easy to see that. But now let's do something a bit more complicated. Let's not group by gender. So here, let's have a look at this again. We're grouping by sex and combining the height. We're skipping the missing and then finding the mean and calling it height again, okay, as we combine it. So we can do that, but we're going to group instead by year and perform the same operation on the height. And what do we see? What do we see if we run this? Well, I don't know. Can anyone make heads or tails of that? Okay. So one thing I would say is it hasn't really trended up or down. Okay, so it's not like people are getting taller. It's also got some wiggles and some weird stuff going on, and it's not really clear. So this sort of like opens up some interesting questions and makes me wonder what's going on, for example, with this zigzag here. Okay. So something's going strange on the years. Now, the years originally started at 4-year increments and changed to 2-year increments. That's because at some point in time, they changed the Winter Olympics to be not the same time as the Summer Olympics, but 2 years after. Okay. And so what do you think is happening with these zigzags? Well, it's sort of interesting. So the people in the Winter Olympics are actually a different height on average than the people in the Summer Olympics, which is kind of cool. So if we actually now we're going to group by and set not just by year, but we're also going to group by season. So this is a really good thing here. If I was writing all this code by hand with for loops and dictionaries, you know, I might have to completely change my code to allow the fact that there's actually now 2 grouping keys, right? I'd have to have like 2 nested dictionaries or like change the key type of the dictionary or something. It'd be a pain in the butt. Yes, at the back. Yes. Yes. So there's like, I think there are some SQL kind of adapters. So you can like make a query and it'll bring the data frame down in Julia. Yeah, so I think like query is designed around the fact that you can define your query in Julia and then convert that to SQL and send that to the database. Yeah, and so that's based on something Microsoft did called Link, which is a part of C#. If anyone's ever used, you know, .NET and C#, it's sort of like an idea from 10 years ago or something. I can't remember. C#3. Yeah. Yeah, but like I was saying, like the really nice thing about data frames is like you can just like, oh, I want to add another column there and figure out how to do the algorithms on the inside for you. Same with SQL, right? SQL has that same property. And so again, this second line is exactly what it was before, and now the plot's slightly more complicated just because we want to have two different colors and some labels and stuff. That's the only reason. And so, you know, they sort of bump around a bit, but generally the winter games are less than the summer games. And what's really happened is there's no zigzags. There's none of this funny high frequency zigzag here. It's gone away. Okay. So we saw something in the data. It led to some questions. It let us sort of plot the data a different way. Now, if you look at these, do you think the people are getting taller or not getting taller over time? Doesn't really look like it. There's no strong signal here at all. Okay. So that's interesting. Maybe there's a very slight slope. I'll give that, but it's not as significant as I expected. So this is cool. So one thing we notice is like actually the type of sport might affect the average height of the competitors. So if you think about basketball, what does basketball select for in terms of basketball players? Height. Like if you're tall, you know you get encouraged to play basketball because you're going to have an advantage over everyone. But you know, winter games, you know, generally single player. A lot about agility and things like that. Probably the heavier you are, probably the harder you fall. Probably a bit of a factor there. So on average, the winter competitors, probably just from the self-selection of each sport, they don't have to be as high to be as tall to be competitive, right? Doesn't help if you come from Brisbane and you're short. It doesn't really help you out, but you know, maybe if you come from Canada. So the second confounding factor, so other than the winter and summer games, actually has to do with women becoming more prevalent. Okay, so I said at the beginning that women were about a third of the competitors, but actually, if we split by year, season, and gender, we actually start to see some more things. So again, the second line of code is exactly the same. So like these packages let you like fiddle around and change your analysis with just like a few touches of the keyboard, and you can get completely different results. So they're really cool. And so now we plot 4 different colors: summer female, summer male, winter female, winter male, right? And first off, you can see they're all quite different heights. Okay. But the other thing, if you look at every single line, they're all 5 centimeters less on the left than on the right. Okay. So let's go back to that first plot. There is no 5 centimeter difference. Maybe you could argue there's like a centimeter in there or something, maybe, right? Here you might argue maybe there's 2 centimeters in it if you're being generous, all right? But in reality, actually, everyone's height's grown by 5 centimeters if you account for the type of games, the year, and the sex. So, and there could be more confounding factors. So what's happened here? What's going on here? Has anyone got any reasons why the fact that when we split the data, that all the curves are going up, but when we combine the data, they're all flat? Anyone have any idea why that might be true? How that could even be possible? Like if you add increasing lines, shouldn't they stay increasing? Yes.
Because increasing is more women.
Yeah, it's the ratio of these things. So the men and the women getting taller, but the women are becoming more relatively numerous compared to the men. And so on average, the averages stay the same. It's kind of cool. So I actually stumbled across this one last year when I was preparing these slides. I was like just fiddling with this. I was like, oh, this is cool. So I just thought this would make a sort of a fun little end to the unit. Now, are there any other things that might have changed in the Olympics over the last 100 years that people could think of that might affect the heights? A lot of sports become professional. So I think this is the self-selection thing. So like basketball was the example before. I think people 30 years ago were really commenting that it suddenly became important to be tall, whereas previously people could be all different heights. So like in the NBA, for example. So I think the fact that everything's become hyper competitive, maybe it's selecting to the extremes a little bit more, the outliers. Yeah, I got another one maybe. So I'm imagining like we saw before that America was had the most athletes contributing, right? If I imagine in my head the Olympics of 1900 and 1904, I'm imagining it's going to have an awful lot of white people, right? And these days it's more international. You'll have people from different continents. There might be different kind of trends and stuff emerging from that too. So you might split this down further and you might find everyone's grown 10 centimeters. I don't know. And have they really grown? I mean, it's a combination of the fact that people were shorter due to nutrition, and then the fact that it's more competitive has changed. The self-selected the competitors in a way. And then, of course, the two things that were really important about separating the genders and okay. So it's easy to verify something like number 3, that women have become more prevalent over time. There was almost none in the early days, and now they're at 40%. So, you know, still closing that gender gap apparently, but here we are. Yeah. So, but just it's interesting. Like, there's a few studies like this where there's a hidden correlation where, like, it was something. I think it was something like, you know, going to Harvard or something was, you know, or some educational thing in America. Doing something for your kid was really important, but if you're correct for all the stuff, it didn't matter, or something like that. There's like been all these sorts of things, and it's kind of really good having these tools where you can kind of like just get in and analyze the data. You know, is this really true? What about this? And you can, with these tools, you know, it's much better than Excel or something. You can just get in and answer that stuff yourself. Julia, of course, and Python and R have excellent plotting packages, so you can like see the histograms of heights. So it's not always just the mean height that's important. You know, there's a distribution, there's a spread. You can kind of break this down. You can break this down over time. You can make a movie of this over years, and you can see the things shift to the right. It's all sorts of cool things you can do. Okay, and there's like 100 more questions we ask. You know, if we figured out for each country, it's the socioeconomic factors of that country in that year, right? Such as GDP per capita or something, right? Can we look at like how competitive they are, how many medals they get, you know, or is the athlete height correlated with their wealth, or is the number of gold medals correlated with their wealth? What about the distance between the Olympics and the home nation? For example, you know, Sydney 2000, Australia won an outsized number of medals compared to other years. So there's a lot of home advantage, and like just more competitors turn up. And then this leads into Unit 8. So like, can we actually predict roughly like the medal counts we might expect at the next Olympics based on things like how everyone's population has changed, how this country's wealth have changed, and like, you know, what are the trends for all the different countries and how well will they all do relative to each other? That's kind of cool. So, yeah, I don't know if anyone has any more questions about data frames they want to throw at me before I talk about one more thing. But yeah, like I said, I think these data tools are super important. Playing with data is really fun. I really enjoy like having just gigabytes of data and just being able to power through it and figure things out. It's sort of like, it's a cool skill. And you can really use your sort of quantitative skills and put them to fit whatever purpose you want, right? And so having tools at your fingertips is really important. So I do encourage you, each and every one of you, go out and learn some of these tools, because you will find it useful on Monday. They're can be used like in research, but also in the real, like in the industry kind of applications as well. So, okay. All right, so this is maybe a bit of a footnote to the data unit. So I did mention, you know, it's always fun to have gigabytes of data. I think I mentioned in the break in the room here, there was a discussion, a complaint, let's say, that the Project 2 simulation might take 20, 30 minutes to complete. And I sort of responded with, well, you know, when I was doing research, it was common. I'd just spin up 200 computers and make them run for 2 weeks, you know, and they would each have, you know, they'd need gigabytes of RAM and like averaging the data and all this sort of stuff, right? So when you're dealing with data, there's sort of like 3 different sizes of data that you tend to need to worry about when you're dealing with data. Okay, there's what we call small data. Okay, small data is data which will load in RAM. Okay, and this is easy. If you have small data, I highly encourage you just to load it in something like Julia and use data frames. It's perfectly fine. Cool. And if you're writing software, you know, there's plenty of like in-memory databases and things like that that you might use, or you might just use data structures in RAM for your applications and things. Medium data is another category. So this is distinct in that you can't fit it all in the RAM, but you can actually fit it on your hard disk. So this computer that I'm on, I think it has 32 gigs of RAM, but it has a terabyte of hard disk, something like that. And you know, other computers might have 8 gigs of RAM, but 256 gigs of hard disk. You know, it depends on the computer, but there's always probably going to be more hard disks than computer. Is there a question? Yeah, okay. So just to remind you, RAM is volatile memory. Whenever you turn it off, it all gets reset back to 0 bits, and it's very fast. So it's random access memory. So your computer turns on, there's data on the hard disk, right? And the operating system loads, and it will load bits of data from the hard disk into the RAM, and the CPU is talking to RAM. So the CPU, you know, when you have anything on your screen, like all the pixels that I see on my screen, everything's in RAM somewhere. And that's RAM is really the only thing the CPU can really deal with directly. Like if you want to add numbers or something, it uses a pointer, it goes to address in RAM, it gets that value, it gets some other value, it brings them down, adds them, and then gets a third pointer and stores it somewhere in RAM. And that's how a computer works. And then there's hard disks, which are like a device. So the CPU can issue instructions, and tell, say, the bus or the motherboard to send an instruction to this device, and then that device will send a message back. And so like the hard drive on your computer is almost like a separate device, which is asynchronously talking to the core part of your computer, which is like the CPU. Right. And so the CPU can send messages to the hard drive and vice versa, but they're kind of a little bit decoupled. There is this idea of like memory mapped IO, which tends to mitigate that a bit, but it's still true. Like that, it's still fundamentally about sending messages back and forth between different devices. Things which are fundamentally different devices, they run on different frequencies. They message each other asynchronously. And so, you know, the hard drive is the bit I could take out of this computer and put in another computer and turn it on, and it'll sort of behave like this computer. But hard drives are a lot slower than RAM, or your SSDs are a lot slower than RAM. But what we can do is like load up a chunk of data from the disk, put it in RAM, process it, save it back to disk, load up the next chunk into RAM, process it, save it back to disk. Eventually, once we've done enough chunks, we might be finished. Maybe the chunks that we save are small. We might need to average the chunks or combine the chunks in some way. So imagine like these group data frames, right? You could imagine each of those group data frames is a file on disk, and you kind of like, you do some analysis on each group independently, you save those results, and then you aggregate all those results and put them together. And that might be something you can do. You might be able to fit that final result RAM, for example. And there's lots of interesting things. So, well, first thing to mention is Julia can do that too. There's packages, I think Dagger or something. There's different ones that help out with this kind of processing and with data frames, group data frames, like I said. When you start going from 1 to 2 and 2 to 3 here, you've got to worry about more things. Like if it's going to take a while, like you might have multiple steps. You might have to process all the chunks and save answers, and then process them again and save answers, and process them and save answers. And you kind of got this data pipeline where you got step 1, step 2, step 3 and stuff. And what you do in this pipeline, for example, is you might, instead of restarting from scratch, if something goes wrong, you might start at like step 2 of your pipeline and then go from there and things like that. And so, you know, as you go down here, your systems tend to get more complicated because you have to worry about faults because the jobs are taking longer, right? And so this thing where you have a lot of data, but it's on disk, is generally the realm of SQL databases, for example. Most SQL, like Postgres or something, you might store on a computer. You might have many terabyte hard disk, and it might serve a very large business or something. Yeah. And then there's the third category, which is called big data, which is data which is too big to fit on the hard drive of a single computer. So what on earth do you do then? Well, you create a distributed system. Like you have all these different computers that can talk to each other. Now, this makes the system a lot more complicated because 2 computers can't talk to each other instantly. There could be a delay. And the messages go over a network, and that delay could be a millisecond, it could be a minute, it could be an hour, and you just don't know what it'll be. Messages are more likely to get corrupt. There's going to be, if your distributed system is big, you might have like hundreds of computers, and there may actually be a reasonable chance that one of them crashes during your computation. Right? Like your computation could be so big that you expect 20 computers to die before it finishes. So your system, your distributed system, has to know how to turn off and on computers while it's computing things and still get to the answer, still get to the correct answer. Okay, so, you know, if you can do things with small data, you don't have to worry about anything like that. Highly recommended. But this is sort of like definitely big bucks for the last decade or two. It's like the whole big data platforms of the cloud providers like Amazon and Google and Microsoft. Yeah. And it's interesting, like what used to be big data, for example, might be small data now. Like I was saying, this data set we're playing with would have been big data in the 80s and would have required multiple computers working together and stuff. One thing, my claim to big data, my most experience with big data is at a company called Fugro. We process literally petabytes of LiDAR data. So LiDAR is like radar, but laser beams. So if I shoot a little laser beam over there and it bounces back, you get a little signal which says, okay, it took 3 nanoseconds to go over there. And then you multiply 3 nanoseconds by the speed of light and you get the distance. Okay. Now, if you do this millions of times a second and you're scanning around, you can actually make like a 3D map of the room, or in this case, they're putting them on the bottom of Cessnas, on the bottom of planes. It scans this way, the plane goes that way, and you end up making like a 3D map of the ground. And we were looking at power lines and problems with the power network for Energy Queensland and other companies in other states and countries. So if you think about Queensland, there's actually something like 250,000 kilometers of power lines just in this lower voltages, the distribution network alone. And any of them could have poles which are leaning, wires that have fallen off, trees that are touching are going to start a fire and things. And you know, those companies have a responsibility to not hurt people, not start fires, not electrocute people driving trucks and stuff like that. So they spend a lot of money previously driving around looking at it, and the new way of doing it was to fly planes to look at it for you. And we wrote algorithms that would like go over, you know, to say tiles in 2D of data and like look what's in that tile and put together the whole network over the whole state and things like that. And so that product had just as much effort put into just shuffling around the huge amounts of data and turning on and off the computers required and things. There's just as much effort to put in that side of things as, which is called data engineering, to the side of things where you're looking inside a bit of data and you're trying to find where a power line or a tree is and how they're touching, and like, you know, those kind of the skills you'd think of doing as a sort of, you know, mathematical modeler, modeling the real world kind of thing. And so, you know, it's sort of interesting where you kind of like, I think there's a lot of fun to be had in this space where these two things are intersecting. Got this like big data engineering, and you got this like really advanced sort of machine learning and different things going on. Anyway, I hope that's kind of a sort of actually we're going to skip that. We're not going to do that. I don't have that prepared. Yeah, I hope that's sort of being interesting for you guys. If it wasn't interesting, I hope it's useful for you one day. Just to remind you that that's going to be part of project 3. So we've sort of split these two into 2 different units. So unit 7 is just about like getting the data and manipulating it. And unit 8 is really going to be like, you know, based on some data, can we predict future data and things like that? So this is like an interesting field. In project 3, you're going to actually need to do that. Like in a real workload, you're going to have to get some data sets. And so you're going to like get some data, you're going to explore it using things like dataframes, right? And it's going to be, this is, Yoni will do another nice video, I'm sure. You're going to like look at some data, which isn't athletes and Olympics, it's going to be like houses and different postcodes and things. And we'll do some analysis and some visualization, like I showed you the histogram and things. You can spend some time learning how to like visualize things in 2D, for example. And then once you sort of have a handle on the data, we're going to use that data to make machine learning models and run predictions. This is on, I think it'll be something like the price of houses or something. I think, is there also, okay. Anyway, so I think that project hasn't actually, so what I clicked on may or may not be the final version for this year, just keep in mind, because it was mentioning that too. Is Matilda giving a talk this year? Okay. Oh, okay, excellent. Okay, all right. No, fair enough. Yeah. So, like I said, this should be some of the content. I'll hang around the Wednesday sessions for the I can't remember the word, the consultation hour. So I'll help with that. Yoni's flying back to Australia this week. He'll be giving a few hours of lectures on machine learning next week. So hope you all look forward to that. That'll be fascinating. That's always a really interesting topic. So it's really kind of like capstone of the whole thing, I think. Yeah, but from my point of view, I hope you enjoyed the course so far. So thanks. So